Right now, without a sound, light is racing across the universe at almost 300,000 kilometers every second, fast enough to circle the Earth more than 7 times before this sentence ends. Nothing catches it. Not a rocket, not a particle, not gravity itself. For centuries we assumed that was simply how light behaves, a quirk of something that glows. But the truth is stranger, and once you see it, you cannot unsee it. That speed is not a limit on light at all. It is the limit on cause and effect, the fastest that anything, anywhere, can ever make anything else happen. And when Richard Feynman looked closely at why nothing can break it, he did not find a wall. He found something far more quietly astonishing hiding underneath. So what is really stopping us, if there is no wall there at all? Get comfortable and let yourself settle in. Subscribe if you have not already, and stay with us, because the answer winds through 4 centuries of people trying to catch light and failing, before it arrives somewhere almost no one expects. Let's get into it. Part 1. The number that refuses to change. Right now, in the small stretch of time it takes you to settle in and get comfortable, light has already crossed the entire planet more times than you could count on both hands. It moves at roughly 300,000 kilometers every second, which is fast enough to loop around the Earth about 7.5 times before a single second has finished passing. It crosses the distance from the sun to your eyes in a little over 8 minutes. It travels from one side of an ordinary room to the other so quickly that no clock you have ever held could catch the delay. And for almost all of human history, people assumed this was simply a fact about light, in the same casual way that we say water is wet or that iron is heavy. I want to start there, with that assumption, because it is so reasonable and so comfortable, and because it turns out to be quietly, profoundly wrong. When we say the speed of light, the words themselves point us in the wrong direction. They make it sound like a description of one particular thing, a measurement of how fast a certain kind of glow happens to move, the way we might measure how fast a car goes or how quickly a river runs. But the number we're talking about tonight is not really about light at all. Light just happens to be the most familiar thing that travels at it. The number is something far stranger and far more fundamental, and by the time we reach the end of this, I think you will never look at an ordinary sunbeam the same way again. Here is the first hint that something unusual is going on. In everyday life, speeds add together in a way that feels obvious. If you are walking forward through a train at a few kilometers an hour, and the train is moving at 100, then to someone standing on the platform you're moving at 100 and a few. Throw a ball forward from a moving car and the ball's speed and the car's speed combine. Walk into a strong wind, and the air seems to rush at you faster than it would if you were standing still. This is how the world works, or at least how it seems to work, and every one of us carries this rule of thumb around without ever thinking about it. It is baked into our intuition so completely that it feels less like a rule and more like common sense itself. But light refuses to obey it. When careful people finally learned to measure light with real precision, they found that its speed never adds and never subtracts. It does not matter whether you're racing toward the source of the light or fleeing away from it. It does not matter whether you measure it in the morning or at night, in one season or another, moving one direction through space or the opposite direction. Light always arrives at exactly the same speed, indifferent to how you move, as if it simply does not care about your motion at all. That single fact, once it was nailed down beyond any doubt, would go on to tear apart the foundations of physics and rebuild them into something almost no one was prepared for. And there is one more thing that makes this number so peculiar, something we will spend most of our time together circling back to. This speed is not just fast. It is a hard ceiling. Nothing that carries mass, nothing you could ever hold or build or become, is allowed to reach it. You can get closer and closer, spending more and more energy, and the universe will keep letting you edge nearer, but the final step is forbidden in a way that no amount of engineering can overcome. It is not that we have not built a good enough rocket yet. It is that the barrier is woven into the structure of reality itself, and understanding why is the whole point of this journey. For now, I only want you to sit with the mystery. We have a number that seems, at first, like a simple property of light, and yet it behaves like nothing else in nature. It refuses to combine with other speeds. It stays the same for everyone, everywhere, no matter how they move, and it forms an absolute wall that nothing with mass can cross. Those are three very strange properties for what we were told was just the speed of a glowing thing. Consider each of those properties again, slowly, because none of them is the kind of thing a mere speed should do. A speed that refuses to add or subtract is like a runner who moves at the same pace whether you chase after them or flee from them, whether you sprint toward them or ride away on the fastest train ever built. A speed that comes out the same for every observer, no matter their motion, is like a distance that measures the same to a person walking and a person standing still, which ought to be impossible, because a speed is only a distance divided by a time. And a speed that forms an absolute ceiling, a rate that nothing with mass can ever quite touch no matter how much energy you pour in, is unlike any speed limit you have ever known, because ordinary speed limits are made of laws and painted signs, and can always, in principle, be broken. This one cannot. And here is the quietly astonishing part. You are soaked in this number every waking second and you never feel it. The light bouncing off the world around you reaches your eyes before any signal about it could travel from your eyes to your brain. When you look across a room at someone, you are seeing them not quite as they are now, but as they were the smallest sliver of a moment ago. The time it took light to cross the space between you. The delay is far too tiny to notice, but it is real, and it never stops. Every image you have ever seen has been a message from the past, arriving a little late, because light, fast as it is not infinitely fast. We will build the entire rest of this story on that one humble fact, and by the end it will have grown into something that stretches from the smallest particle to the far edge of everything we can see. When a single number behaves this consistently, this stubbornly, across every experiment anyone can devise, it is usually a sign that we're not looking at a detail. We are looking at a load-bearing pillar of the universe, and we simply did not recognize it. That recognition did not arrive all at once. It came slowly, painfully across centuries, built by people who were mostly trying to answer a much smaller and more innocent question. They were not trying to overturn our understanding of time and space. They were just trying to find out how fast light goes. What is remarkable is that the answer to that modest question kept getting stranger the harder anyone looked, until finally two of the most careful minds who ever lived, Albert Einstein and Richard Feynman, would each take a turn at it and hand us back a universe we barely recognized. Einstein would show us how the speed limit works, in exquisite and unforgiving detail. Feynman would go one step further and show us why it exists at all, and his answer is so strange and so beautiful that it is the reason we are here tonight. But to feel the full weight of what they found, we have to go back to the beginning, to a time when nobody even knew whether light took any time to travel at all. We have to go back to a hillside in Italy, to a man holding a lantern in the dark, trying to catch something that was already far faster than he could possibly imagine. Part 2. The Man on the Hill. The story begins not in a laboratory full of instruments, but on a quiet hillside outside the city of Florence, where one stubborn man decided to try something no one had ever managed before. In the year 1638, Galileo Galilei set out to measure the speed of light with nothing but 2 lanterns, an assistant, and his own considerable patience. It sounds almost charming now, almost naive, but you have to understand who this man was and what he had already done to appreciate how serious the attempt really was. Galileo was by this point one of the most dangerous thinkers alive, dangerous in the sense that he kept overturning things people had believed for 1,000 years. He had turned a telescope toward Jupiter and watched 4 little points of light circle it night after night, proving that not everything in the heavens revolved around the earth. He had rolled balls down ramps and worked out that motion followed simple, universal rules that did not care whether you were a king or a stone. He had a habit of taking questions that everyone assumed were settled or unanswerable and dragging them into the light of actual measurement. So when he turned his attention to light itself, he did it in the only way he trusted, by trying to time it. His plan was simple and on paper beautifully logical. He and an assistant would climb 2 distant hilltops, each carrying a lantern with a shutter they could open and close. Galileo would uncover his lantern, sending a flash across the dark valley between them. The instant the assistant saw that flash, he would uncover his own lantern in reply. Galileo would then measure the time between the moment he opened his shutter and the moment he saw the answering light come back. Knowing the distance between the hills, he could divide distance by time and, in principle, calculate exactly how fast light had made the round trip. It is the same basic idea we would use today to time a returning signal or to bounce a pulse off a distant object. The reasoning was sound. The trouble was that the universe was hiding something Galileo had no way to anticipate. No matter how far apart they placed the hills, the answering flash always came back instantly. There was no gap he could measure, no hesitation, no delay of any kind. The moment he opened his lantern, the reply seemed to arrive in the very same instant, as though the light spent no time at all crossing the valley. He tried again and again. He pushed the hills farther apart. He accounted for how long it took his assistant to react. He repeated the whole exercise, patient and methodical, and every single time the result was the same. The light came back so quickly that the only delay he could ever detect was the sluggishness of human reflexes, the slow fumbling of a person reacting to a flash, and nothing more. Now here is what I find so admirable about Galileo, and it is a quality we will see again and again in this story. He did not force an answer. He could easily have declared that light was simply instantaneous, that it took no time to travel, and many people of his era would have nodded along. But he was too honest for that. He recognized exactly what his failure meant. Either light truly did move infinitely fast, or it moved so incomprehensibly fast that no experiment done between two hills on Earth could ever hope to catch it. He suspected it was the second. He suspected there was a real speed there, a finite one, hiding just beyond the reach of his lanterns, but suspicion he knew was not proof, and he refused to pretend otherwise. I want you to stand on that hill with him for a moment, because it is a scene worth living inside. Picture the night air, cool and still, the kind of dark that existed before cities glowed. You're holding a lantern, its metal warm against your palms, its shutter under your thumb. Far across the black valley there is a single point of light where your partner waits, so distant it trembles slightly in the air. You take a breath, you lift the shutter, and in the instant you do, before your breath has even finished leaving you, the answering flash is already there, already blazing back at you from across the valley as if it had been waiting. There is no gap to feel, nothing to time, nothing your senses can grab onto. You are a careful man holding a careful instrument, and the thing you are chasing has just slipped past you faster than your own nervous system can register. You're trying to time a whisper using a clock that ticks like thunder, and some part of you begins to understand that the problem is not your patience. The problem is that you are far, far too slow, and so is everything you have to work with. That image is worth holding on to because it captures the real obstacle. Galileo had been trying to measure a whisper with a clock that ticked like thunder. His hills were a few kilometers apart at most, and light crosses a few kilometers in a handful of millionths of a second. A span of time so short that the fastest human reaction is slower by a factor of tens of thousands. He never had a chance, and the astonishing thing is not that he failed, but that he understood so precisely why he failed. To feel how hopeless his task really was, put some numbers to it. Light crosses the few kilometers between two hilltops in something like 100,000th of a second. A span of time so brief that calling it an instant is generous. The fastest a human being can react to a sudden flash, the very quickest the eye can see and the hand can move, is around 1/10 of a second. That means the delay Galileo was hunting for was smaller than his own reaction time, by a factor of tens of thousands. He was not close. He was not even in the neighborhood of close. He was trying to measure the thickness of a single hair, with a ruler marked only in miles, and no amount of patience or care could shrink that gap. But notice what he managed to accomplish anyway, because it matters. He did not walk away believing he had proven light to be instantaneous, which would have been the easy conclusion and the wrong one. He walked away having established something subtler and more honest, that whatever the speed of light was, it was so enormous that catching it would demand distances far greater than anything two people with lanterns could ever arrange. He had turned a failed measurement into a genuine piece of knowledge, a flaw beneath the speed of light and a signpost pointing toward where the answer might someday be found. There is a kind of scientific courage in that, in refusing to claim more than the evidence allows, in being willing to say I could not measure it rather than pretending you had. It is a quality we will see again in every person who moves this story forward, because the temptation to force a tidy answer is always there, and the universe has a way of punishing those who give in to it. He had correctly identified that light was simply operating on a scale of speed that dwarfed anything human beings could measure with the tools of muscle and eye. To catch it, you would need distances far greater than any two hills could offer. You would need, though he could not have known it, the sky itself. And this is where the human stakes of the whole question first come into focus. Galileo was not just measuring a number. He was discovering that there are things in the universe that move faster than we can perceive, faster than we can react to, faster than our bodies were ever built to handle. When you flip a switch and a room floods with light, that light reached your eyes before any signal from your fingertip could even reach your brain. We live our entire lives bathed in something that outruns our own senses, and we almost never notice. Galileo noticed. He stood on a hill and tried to catch it, and in failing he became the first person to feel, in his own hands, just how fast the universe can actually move. He would not live to see the answer. The tools of his lifetime were simply not enough. But the question he could not close did not die with him. It waited patiently for someone to look in the right place, at a scale so enormous that even light would finally reveal its delay. And when that answer came, it would not come from a hill or a lantern at all. It would come from a distant moon sliding into the shadow of a giant planet, keeping a kind of time no one had thought to read. Part 3. A Clock Made of a Moon. The answer that eluded Galileo arrived a few decades later, and it came from the last place anyone was looking, from the clockwork motion of a small moon orbiting a giant world. It was found not by building a better lantern or a faster shutter, but by watching the heavens with enough patience to notice that something was subtly, persistently wrong. In the 1670s, a young Danish astronomer named Ole Rømer was working at the observatory in Paris, and his assignment was about as tedious as astronomy gets. He was tracking the eclipses of Io, one of the 4 moons Galileo himself had discovered circling Jupiter more than half a century earlier. Io swings around Jupiter quickly, and on each orbit it slips behind the giant planet and vanishes into its shadow, then reappears on the other side. These disappearances and reappearances happen with such regularity that astronomers of the time treated them like a giant clock hanging in the sky. If you knew the rhythm of Io's eclipses, you could predict them far into the future, and you could even use them to help solve practical problems, like figuring out your longitude at sea. Rømer's job was to time these eclipses carefully and refine the predictions. It was the kind of patient, repetitive work that reveals nothing to a careless observer and everything to a careful one. At first, Rømer saw nothing strange. But as the months passed and the Earth carried on its slow journey around the Sun, a pattern began to surface, and it was a pattern that made no sense under the assumptions of the day. The eclipses of Io were drifting off schedule. When the Earth was on the side of its orbit that brought it closer to Jupiter, the eclipses arrived early, ahead of the predicted time. When the Earth was on the far side of its orbit, moving away from Jupiter, the eclipses ran late. And this drift was not random. It tracked, cleanly and precisely, with how far the Earth was from Jupiter. Over the course of half a year, as the distance between the 2 planets grew to its maximum, the accumulated delay added up to around 22 minutes. Most astronomers, faced with this, shrugged and reached for the usual explanations. Perhaps Io's orbit was a little irregular. Perhaps Jupiter's enormous gravity was tugging on the moon in ways the math had not quite captured. There are always small imperfections in any model, and it is easy to file an anomaly away as one more thing to be cleaned up later. But Rømer looked harder, and he rejected those explanations because the pattern was simply too tidy, too perfectly linked to one specific thing, the changing distance between the Earth and Jupiter. When a discrepancy lines up that neatly with a single variable, it is trying to tell you something, and Rømer was willing to listen. In the year 1676, he proposed an explanation that was as bold as it was simple. The eclipses, he argued, were not actually happening early or late. Io was sliding into Jupiter's shadow exactly on schedule, right on the beat, every single time. What was changing was the time it took for the light carrying the news of each eclipse to travel across space and reach the Earth. When the Earth was closer to Jupiter, that light had a shorter distance to cross, so it arrived sooner. When the Earth was farther away, the very same light had a longer journey, so it arrived later. The eclipses only looked like they were drifting because we were watching them from a moving platform at constantly changing distances, and light took real, measurable time to bring us the picture. This was the breakthrough Galileo could not reach. Light was not instantaneous after all. It had a finite speed, and now, for the first time, someone had caught it in the act of taking its time. Rømer even used his numbers to estimate how fast light must be going. He took the diameter of the Earth's orbit and divided it by the accumulated delay, and he arrived at a value for the speed of light. By modern standards, his answer was off, low by around 25%, hobbled by the fact that nobody yet knew the true size of the Earth's orbit with any precision. But the exact figure hardly mattered. What mattered, what changed everything, was the proof that light took time to travel at all. Information itself, the news of an event, could not arrive instantly. It had to cross the distance, and crossing took time. Sit with that idea, because it is one of the most quietly staggering realizations in all of science, and it follows directly from what Römer found. If light takes time to reach us, then everything we see is to some degree a picture of the past. The sun you see is not the sun as it is right now. It is the sun as it was about 8 minutes ago, because that is how long its light takes to reach your eyes. If the sun somehow blinked out this instant, you would go on seeing it, warm and ordinary in the sky, for another 8 minutes before the darkness arrived. Jupiter, when you find it as a bright point in the night, appears to you as it was the better part of an hour ago, and the farther out you look, the further back in time you're seeing. The stars scattered across the night are showing you light that left them years, centuries, sometimes thousands of years ago. There is a practical side to Römer's discovery that is easy to overlook, and it grounds the whole thing in something very human. The regular eclipses of Jupiter's moons were, at the time, among the best clocks available to anyone trying to solve the great navigational problem of the age, the problem of knowing your longitude at sea. If two observers in different places could both watch the same eclipse and compare their local times, they could work out how far apart they were around the globe. Römer's finding that the timing of those eclipses depended on how far the light had to travel to reach you was not merely a philosophical curiosity. It was a correction that mattered to mapmakers and navigators, a reminder that even our clocks in the sky arrived with a built-in delay. But the far larger consequence was the one that reaches all the way to us tonight. Once you accept that light takes time to arrive, the entire night sky rearranges itself in your mind. It stops being a flat ceiling of points all shining at once, and becomes something more like a stack of old letters, each written at a different moment and only now being opened. The light from a star 1,000 light years away has been travelling since long before you were born, since before your great-grandparents were born, carrying a picture of that star as it was 1,000 years ago. You cannot see the star as it is now. You never can. You can only ever read its old mail, and the mail is always out of date. To look up, then, is to look back, and there is no telescope powerful enough to change that, because the delay is not a shortcoming of our instruments, it is a feature of the universe itself. Looking into space, it turns out, is the same thing as looking into the past. There is no way around it. The finite speed of light means the night sky is not a snapshot of one moment. It is a layered picture of many different times, all stitched together and arriving at your eye at once. This is the second callback I want to plant in your mind, alongside the whisper and the thunderous clock from Galileo's hill. Looking into space is looking into the past. Hold on to it, because much later, when we stand at the edge of everything we can see, that simple phrase is going to open up into something enormous. And notice what has happened to our central question. We started with what seemed like a property of light, a speed, and Römer has just shown us that this speed does something no ordinary property should do. It sets a delay on reality itself. It means the universe comes with built-in lag, that no event anywhere can announce itself to the rest of the cosmos instantly. That news of anything must crawl outward, fast but not infinitely fast, taking real time to arrive. The sun's warmth on your face is 8 minutes old. That is not a limitation of your eyes or your instruments. That is a rule about how the universe delivers information, and it is starting to look less like a fact about light and more like a fact about everything. Römer had cracked open a question Galileo could not close, and in doing so he had handed humanity a new and unsettling relationship with the sky. But he had also deepened the mystery rather than solving it, because now there was a specific speed, a real and finite number, and a new question rose immediately behind it, sharper than before. Why this speed? Why should light travel at this particular rate and not some other? What in the structure of the universe reached in and fixed that number so precisely, and held it so firmly that it would refuse to change no matter who measured it, or how? To answer that, physicists would spend the next 2 centuries chasing light with ever finer instruments, until one of those experiments returned a result so impossible that it broke the physics everyone thought was finished. Part 4. The Wind That Wasn't There. By the end of the 1800s, physics felt almost finished. like a cathedral with only a few small stones left to set in place. Motion followed the laws that Newton had written down 2 centuries earlier. Space was imagined as an invisible grid, stretching out forever in every direction, the same for everyone. Time was thought to flow at one steady universal pace, a single great clock ticking away in the background of existence, identical whether you were standing still or racing across the world. And light was understood to be a wave, one more ripple travelling through the universe, distinguished only by the fact that it happened to move extraordinarily fast. Physicists of the era were genuinely proud of how complete their picture had become. A few of them even suggested out loud that the great work was nearly done, and that future generations would spend their careers merely refining the decimal places. There was, however, one loose thread, and it had to do with that word, wave. Every wave anyone had ever studied was a disturbance travelling through some medium. Sound is a wave of pressure moving through air, and if you remove the air, the sound has nothing to travel through, and it simply cannot exist. Ocean waves need water. Ripples need a pond. So if light was a wave, physicists reasoned, then light too must be a disturbance in something, some substance filling all of space that could carry it along. They gave this substance a name. They called it the luminiferous ether, the light-bearing ether, and they imagined it as an invisible material soaking through the entire universe, present in the emptiest reaches of space and passing straight through solid walls, so thin and frictionless that planets could sail through it without slowing, yet somehow rigid enough to carry light waves at their tremendous speed. It was a strange thing to believe in, a substance you could never see, touch, or feel, but it seemed logically unavoidable. Waves need a medium, light is a wave, therefore the medium must exist. The reasoning felt airtight, and the ether made a very specific, very testable prediction. If it filled all of space and stood still, then the Earth, hurtling around the Sun at roughly 30 kilometers every second, must be moving through it. That motion should create a kind of wind, an ether wind, in the same way that sticking your hand out the window of a moving car creates a rush of air even on a still day. Light travelling with that wind should move a little faster, and light travelling against it should move a little slower, and light crossing it sideways should behave differently still. The effect would be tiny, a small difference riding on top of an enormous speed. But by the 1880s, physicists had finally built instruments delicate enough to detect it. All they had to do was measure light speed in different directions and watch for the shift the ether wind should produce. In the year 1887, 2 Americans, Albert Michelson and Edward Morley, built an instrument of almost obsessive precision to hunt for exactly that shift. Their device, called an interferometer, took a single beam of light and split it into 2, sending the halves along 2 paths set at right angles to each other. The beams travelled outward, bounced off mirrors, and came racing back to recombine. If one beam had been slowed even slightly by moving against the ether wind while the other had not, the 2 beams would fall out of step, and when they merged they would produce a telltale pattern of light and dark bands, an interference pattern that would shift depending on the direction of the apparatus. To keep the whole thing steady and free of vibration, they mounted it on a massive slab of stone, and they floated that stone on a pool of liquid mercury so it could be turned smoothly in any direction. They measured at different times of day, in different seasons, with the apparatus pointed every possible way relative to the Earth's motion. Their instrument was sensitive enough to catch a difference far smaller than the ether theory demanded, a shift of less than 1 part in 10,000. They found nothing. No shift in any direction, at any time of day, in any season. The light moved at precisely the same speed no matter which way the beam was pointed, no matter how the Earth was racing through space. The ether wind that should have been there, that had to be there if the whole picture of light as a wave in a medium was correct, simply did not exist. It was one of the most important experimental results in the history of science, and it was a resounding, ringing silence. The most careful search anyone had ever mounted for the ether had come back completely empty. The physicists of the time did not surrender the ether easily, and it is worth understanding why they fought so hard, because it was not stubbornness for its own sake. The ether was not an idle guess. It was the load-bearing assumption beneath the entire wave theory of light, and the wave theory had been spectacularly successful, explaining how light bends and spreads and separates into colours. To abandon the ether felt like abandoning everything that had worked. So instead, some of the most respected minds of the era set about inventing ways to save it. They proposed that objects moving through the ether contract in the direction of their motion by precisely the amount needed to hide the wind. They proposed that time itself runs slow for moving systems, again by exactly the right amount. Each patch was mathematically ingenious, and each one worked, in the narrow sense that it made the equations come out right. But a theory that survives only by adding one perfectly tuned excuse after another is a theory in trouble, and some of them sensed it. There is a particular smell to that kind of fix, the smell of an idea being kept alive on machines. Over the following years, the null result was checked and rechecked with steadily improving instruments, and it never once wavered. No ether wind, ever, in any direction, at any precision anyone could reach. The universe was not being coy. It was stating the truth plainly and repeatedly, and the truth was that there was no ether and no wind and no preferred state of motion, only light, moving at its one fixed speed for everyone. The patches were describing something real, but not what their inventors believed. They were the first blurry outlines of a new geometry of space and time, and it would take an outsider willing to trust the measurement over the intuition to see them clearly for what they were. This result did not just fail to find the ether, it struck at the foundations of everything. If light needed no medium, then it was unlike every other wave physicists had ever known. And worse, far worse, was what the null result implied about the speed itself. Light's speed was not adding to the Earth's motion, and it was not subtracting from it. It was staying stubbornly, impossibly fixed, exactly the same regardless of how the observer moved. That flatly contradicted the most basic common sense about motion, the very rule of thumb we started with, the one that says speeds combine. A beam of light aimed in the direction the Earth was travelling should have measured faster than a beam aimed against it. Instead, they were identical, down to the finest precision the instrument could reach. It was as if you could walk toward an oncoming person and toward someone walking away from you, and somehow measure both of them approaching you at exactly the same pace. Physicists were now trapped between two unbearable options. Either the most careful experiment ever performed was somehow wrong, which seemed nearly impossible given how many ways they checked it, or the deepest assumptions about space, time, and motion were incomplete, which seemed almost worse. Many of the greatest minds of the age chose to save the old picture with clever patches. One proposal held that objects physically shrink in the direction they move through the ether, contracting by just the precise amount needed to hide the expected effect, so that the interferometer's arm shortened exactly enough to erase the difference it should have shown. Another suggested that time itself slows down for moving systems, again by exactly the amount required to keep the measured speed of light the same for everyone. On paper, these fixes worked. The mathematics came out right, but they felt deeply artificial, like scaffolding hastily bolted onto a building that could no longer stand on its own. They amounted to saying that nature was performing a conspiracy of perfectly calibrated distortions, bending space and squeezing time by exactly the amounts needed, all for the apparent purpose of protecting one single number from ever being caught changing. And that is the thought that should nag at you, the same thought that nagged at the physicists of that era, even the ones proposing the patches. Why would the universe do that? Why would space and time contort themselves with such uncanny precision, hiding the effect at every turn just to keep the speed of light fixed? A single stubborn number was reaching into the machinery of reality and forcing space to shrink and clocks to slow in perfect coordination, and nobody could say why. Most people, faced with a nuisance like this, will bend the world into knots to preserve what they already believe. It takes a rare kind of mind to look at all that frantic patching and ask a different question entirely. Not how do we save the old picture, but what if the picture is wrong, and the strange behaviour of light is trying to show us something true? The human weight of this moment is easy to miss from a distance of more than a century. These were not fools clinging to superstition. They were brilliant, careful people watching the solid ground of their entire worldview turn to water beneath them. The comfortable universe of one universal clock and one fixed grid of space was dissolving, and the thing dissolving it was the most ordinary phenomenon imaginable, the light we see by every day. Something enormous was hiding inside that refusal to add and subtract like everything else, and it would take an outsider, someone with no reputation to protect and nothing to lose, to stop trying to rescue the old world and simply accept what the light was saying. That outsider was sitting at a desk in a patent office, and he was about to take the speed of light completely seriously, more seriously than anyone ever had, and follow it wherever it led. Part 5. The Clerk Who Believed the Number. In the year 1905, the person who finally broke the deadlock was not a famous professor with a grand laboratory. He was a young clerk in a patent office in the Swiss city of Bern, reviewing applications for gadgets and machines, thinking about physics in the margins of his day. His name was Albert Einstein, and his great move was not to invent some new and clever patch to save the ether. His move was almost the opposite. He simply stopped fighting the strange behavior of light and decided to believe it completely, to take it as a starting point rather than a problem, and to ask what the universe would have to be like for it to be true. Einstein built his reasoning on 2 statements, and both of them sound almost too modest to matter. The first was that the laws of physics are the same for everyone moving at a steady speed. Whether you're drifting through space or sitting in a station, no experiment you perform can tell you your absolute motion, because there is no absolute motion to find. The second was the one everyone had been trying so hard to explain away. The speed of light in empty space is the same for every observer, no matter how they are moving. He did not try to justify why light behaves this way. He took the experimental fact, the one Michelson and Morley had hammered into place, and he elevated it to a principle, and then he followed it with relentless logic, all the way to the end, no matter how absurd the conclusions began to seem. The conclusions were staggering. If the speed of light truly never changes, if it is the same for a person standing still and a person racing toward the source, then something else has to give, because our old common sense simply cannot survive that fact. And what gives, Einstein showed, is time itself. Time does not flow at the same rate for everyone. A clock that is moving genuinely ticks more slowly than a clock at rest, and this is not an illusion, not a trick of measurement, not a mechanical failure in the moving clock. Time itself stretches out for anything in motion. The faster something moves, the more pronounced the effect becomes. At the ordinary speeds of daily life, the slowing is so minute that we never notice it, which is exactly why it stayed hidden for so long. But as you approach the speed of light, it grows overwhelming. Clocks crawl, processes drag out, even aging slows down. Push right up to the edge of light speed and time nearly grinds to a halt. And this single idea, strange as it is, dissolves the paradox that had tormented everyone. Suppose you tried to chase a beam of light, to catch up to it and ride alongside. You accelerate, faster and faster, pouring on speed, certain that eventually the beam must stop pulling away. But it never does, and now you can see why. As you speed up, your own time stretches, your own seconds swell and slow, and the beam continues to race away from you at exactly the same speed as always. It is not that the light accelerates to stay ahead of you. It is that your very experience of time reshapes itself, moment by moment, precisely enough to keep light speed constant from your point of view. You cannot win the race because the finish line moves with the runner in a way that keeps it forever out of reach. There is a lovely detail about where this idea came from, because Einstein had been turning it over since he was a teenager. As a young man, he asked himself a simple question, the kind a curious 16-year-old might. What would a beam of light look like if you could ride alongside it, matching its speed exactly? In the old physics, the answer should be a frozen wave, a motionless ripple of light hanging in the air beside you. But something about that picture bothered him for years, because a frozen light wave is not something the laws of physics permit, and no one had ever seen such a thing. The resolution, when it finally arrived, was that you can never ride alongside a beam of light at all. You can never catch it. The universe is built so that light outruns you at the same speed, no matter how fast you go, and the price of keeping that true is that your own time must stretch. The teenage puzzle and the grown man's theory turned out to be the same question, finally answered. And I want to be clear that none of this is idle speculation or clever mathematics with no bearing on the real world. Time dilation is measured constantly and we depend on it. High in the atmosphere, cosmic rays crash into the air and create tiny particles called muons, which survive for only a couple of millionths of a second before they fall apart. By all rights, they should decay long before reaching the ground. And yet they arrive at the ground in enormous numbers, because they are moving so close to light speed that their internal clocks run slow, stretching their fleeting lives just enough to complete the journey. When physicists have flown atomic clocks around the world on airplanes and compared them to identical clocks left behind on the ground, the travelling clocks come back showing slightly less elapsed time, exactly as the equations predict. And the satellite navigation system that guides you through an unfamiliar city has to correct for time dilation continuously, because the clocks aboard those orbiting satellites tick at a measurably different rate than the ones on the surface. If engineers ignored this, your maps would drift wrong within minutes. The stretching of time is not a thought experiment. It is a daily fact of the machinery running quietly all around you. Let yourself live inside that chase for a moment, because it is one of the strangest things you will ever imagine. Picture yourself sprinting after a beam of light. You're already moving at half its speed, and you strain for more and you get it, 3/4 now, and the beam is still gliding ahead of you at the same untouchable pace it had when you started. You push harder. You can feel, in this impossible dream, your own time thickening around you, your seconds swelling like something heavy and slow, while out in the ordinary world clocks race ahead. You're pouring everything into closing the gap, and the gap will not close. The light does not strain, does not hurry, does not even seem to notice you are there. It simply keeps its distance serene and constant, while the universe rewrites the length of your seconds to make sure it always can. You realize, with a chill, that the race was never winnable, and that the reason has nothing to do with how fast you can go. It has to do with what time is, and what time is turns out to depend on how you move. Space did not escape untouched either. Einstein showed that just as time stretches for moving things, lengths contract along the direction of motion. A moving object becomes shorter, not because it is being crushed by any force, but because space itself measures differently for something in motion. Time and space, which everyone had treated as separate and absolute, the fixed stage on which events play out, turned out to be flexible and interwoven, two aspects of a single fabric that Einstein called space-time. And here is the elegant part, the reason it all holds together. Time dilation and length contraction are not two random distortions. They work in perfect partnership, adjusting by precisely the amounts needed, so that every observer, no matter how they move, always measures light travelling at the same speed. Durations stretch, distances shrink, and the ratio of the two, which is what a speed really is, comes out identical for everyone. The constancy of light is preserved not by luck, not by conspiracy, but by the very structure of space and time. The frantic patches the earlier physicists had bolted on, the shrinking objects and the slowing clocks, were not desperate fixes after all. They were glimpses of the real geometry of the world, and Einstein was the one willing to accept that geometry as the truth. This also meant the ether could be quietly laid to rest. There was no invisible medium to detect because light was never a disturbance rippling through a substance the way sound moves through air. Light was showing us how space-time itself behaves, and Einstein's equations carried one more consequence, one that would prove central to everything still ahead of us. No object with mass can ever reach the speed of light. As you accelerate something, the energy needed to speed it up further grows, and near light speed that energy demand does not just get large, it climbs toward infinity. To actually reach the speed of light, a massive object would require not a great deal of energy, not an impractical amount, but an infinite amount, which is to say, an impossible amount. The barrier is absolute, and it is written into the mathematics of motion itself. Light, of course, manages the speed effortlessly, and now we can see why. Light has no mass. Photons, the particles of light, are not pushed up to light speed by some engine. They are born at that speed and exist only at that speed. For them, in a sense we will return to, no time passes at all between leaving their source and arriving at their destination. They are creatures of the speed limit native to it, while everything with mass is forever locked below it. Einstein had done something almost miraculous. He had taken the maddening, paradoxical behaviour of light and shown that it was not a paradox at all, but the signature of a deeper truth about time and space. His theory predicted the outcome of experiment after experiment with astonishing accuracy, and over the following century it would pass every test thrown at it. And yet, for all its power, relativity answered one question by opening another. It told us, with perfect precision, how the speed limit works. It never told us why the limit should exist in the first place, why the universe is built around this one number at all. To feel that question in your bones, we need to try and fail to break through the barrier ourselves. Part 6. The Wall Made of Infinity. Imagine for a moment that every engineering problem has been solved, and you're sitting in the cockpit of a spacecraft that should not exist. Its engine never runs out of fuel, it never overheats, it converts energy into thrust with perfect, lossless efficiency. There is no friction in space to fight, no air to push through, no practical limit of any kind left standing except the ones written into reality itself. Your task is simple to state, if not to achieve. You're going to accelerate and keep accelerating until you break through the speed of light. And I want you to actually take this trip because feeling how it fails is the only way to understand that the barrier ahead of you is not a wall of steel. It is something far stranger. At first, everything behaves exactly the way your intuition insists it should. You fire the engine and the ship surges forward, pressing you back into your seat, and the speed climbs in a clean and satisfying way. You pass 1% of light speed, then 5, then 10, and every push on the throttle buys you a matching gain in velocity. At 10% of light speed, you're already moving at 30,000 kilometers every second, fast enough to cross the entire width of the Earth in less than half a second, fast enough to reach the moon in a breath. And yet, next to your goal, you are barely crawling. So you keep going. 20%, 30, 40. The relationship between how hard you push and how fast you go stays comfortable and predictable. The universe seems perfectly willing to let you accelerate, and you begin to think this might actually be easy. Then, somewhere near the halfway mark, something subtle begins to change, and it is the strangest thing you have ever felt. The engine is just as powerful as it always was. The fuel is pouring in at the same rate. The thrust pressing you into your seat has not weakened at all, and yet the speed is no longer climbing the way it did. Each additional burst of energy buys you a little less velocity than the burst before it. At first, the shortfall is easy to shrug off. At half of light speed, the effect is noticeable but modest. By 70%, it is impossible to ignore. By the time you reach 90%, the curve has bent hard against you, and the same engine that once threw you forward in great leaps now strains to add even a fraction of a percent to your speed. You're not fighting friction. You're not fighting drag. There is nothing outside the ship to fight at all. You're fighting space-time itself, and space-time is starting to win. Einstein's equations describe precisely what is happening to you. As your speed increases, your resistance to being accelerated further increases along with it. The early physicists described this by saying that a moving object's mass grows as it speeds up. The modern way of putting it is more careful, but the effect is the same. Your momentum climbs faster and faster as you approach the speed of light, and there is a factor in the mathematics that governs exactly how this resistance grows. At low speeds, this factor sits harmlessly close to 1, which is why none of this matters in everyday life. But as you push toward light speed, it begins to swell, slowly at first, then explosively. At half of light speed, it is only about 1.15, so your resistance to further acceleration is just 15% higher than it was at rest. At 90% of light speed, it has grown to about 2.3, so you now need more than twice the energy to gain the same speed you once gained easily. At 99%, it passes 7. Every small step forward now costs 7 times what it used to, and it only steepens from there, relentlessly, without mercy. At 99.9% of light speed, the factor climbs past 20. At 99.99%, it approaches 70. Add another 9, and it surges past 200. Each additional digit of 9s you try to add to your speed multiplies the difficulty by a punishing amount, and the pattern never breaks and never relents. Every step closer to light speed demands wildly more energy than the step before, and the closer you get, the more violently reality resists. And when you finally do the arithmetic for reaching light speed exactly, the factor does not come out to some enormous but finite number. It becomes infinite. The energy required to push any object with mass all the way to the speed of light is not a staggering amount, not an amount beyond our current technology. It is an amount beyond all amounts, infinity itself, and no engine, no fuel, no breakthrough that will ever be invented can supply an infinite quantity of anything. The barrier ahead of you is not a matter of building something better. It is structural. It is built into what energy and motion are. This is not a story confined to imaginary starships either. We watch it happen every single day in real machines. In the most powerful particle accelerators ever built, engineers push protons to speeds within a hair of a light speed, and they run headlong into this exact wall. At a machine like the Large Hadron Collider, protons reach more than 99.9999% of the speed of light, and at that point pouring in more energy barely changes their speed at all. Instead, the energy goes into making them harder to steer, harder to bend around the ring, harder to hold on course. This is why the magnets that guide them have to be so monstrously strong. They are not fighting friction. They are fighting the same refusal of space-time to let anything with mass touchlight speed. The wall is real, and we bump against it in laboratories on Earth, and it never, ever gives. It helps to see clearly where all that energy actually goes, because it is not going into speed. When engineers pour more power into protons already racing at more than 99.9999% of light speed, the protons barely quicken at all. What grows instead is their momentum, their sheer reluctance to be turned or stopped. The quantity that behaves as though the particle were becoming heavier and heavier the closer it creeps to the limit. A proton at full energy in one of these machines carries the momentum of something far more massive than a proton at rest, even though its actual speed has only a whisper of a fraction of a percent left to gain. The energy is real and enormous, and it is buying almost no additional velocity, only a mounting, thickening resistance. That is the true face of the barrier. It is not that we lack a powerful enough engine. It is that the very last sliver of speed, the tiny gap between what we can reach and light itself, would swallow an infinite amount of energy to cross, and infinity is not a sum you can save up for. You could convert an entire star into fuel, then a whole galaxy, then every galaxy in the observable universe, and you would still not have carried a single massive object all the way to light speed. You would have edged a little closer, added another 9 or 2 to the string of 9s, and stopped just as short as before, because there is always another 9, and the cost of each one climbs without end. The wall is not made of anything you could push through with a better machine. It is made of infinity, and infinity has no far side to reach. I called it a wall, and I want you to hold on to that word for now, because it is exactly how it feels from inside the cockpit. You have this magnificent engine, endless power at your command, and out ahead of you there is a barrier you cannot cross no matter what you do, a smooth, invisible surface that the universe will not let you through. It looks like a wall. It behaves like a wall. Every instinct you have says there must be something on the other side of it, some forbidden territory just past the boundary, if only you could break through. Remember that feeling, that image of the wall, because much later in our journey it is going to turn completely inside out, and you're going to see that it was never a wall at all. But we are not there yet. For now, it is enough to feel how absolute the barrier is, and there is more happening to you than just the resistance. As your ship approaches light speed, time aboard slows relative to the outside universe, exactly as Einstein promised. At 90% of light speed, your clock runs at less than half the pace of the clocks back on Earth. A year passing for the people you left behind is only a few months for you. Push to 99% and the gap yawns wider still. For every year you experience, many years sweep past in the world outside. Keep going, and the slowing grows without bound, until at light speed time would stop entirely. This is not a poetic flourish. It falls directly out of the equations. An object with mass cannot exist in a state where its own time has frozen completely, where every internal process, every heartbeat of every atom has been locked motionless in place. And your length would be contracting too, shrinking along your direction of travel toward nothing, so that at the limit you would be compressed into a geometry that cannot exist, an object with no extension at all, yet still somehow containing all its inner workings. Time stops, length vanishes, energy explodes toward infinity. These are not 3 separate problems. They are one problem, seen from 3 directions, and together they reveal something profound. There is no smooth road that carries a massive object from below light speed up to light speed. The equations do not describe a difficult crossing. They describe a bridge that was never built, a gap with nothing on the far side for a massive object to stand on. So Einstein has brought us to the edge of the barrier and shown us, in overwhelming and unforgiving detail, exactly how it holds. He has shown us the swelling energy, the freezing clocks, the vanishing lengths. He has told us, with more precision than almost any theory in history, how the speed limit works. But if you are anything like me, standing at that impossible wall with a limitless engine and no way through, one question burns hotter than all the rest, and Einstein's beautiful equations do not answer it. Not how does the wall hold? Why is it there at all? Why should the universe be built around this one number, so absolutely that it would rather freeze time and crush space to nothing than let anything cross? That question would wait for a different kind of mind, a physicist who did not just want to calculate what the universe does, but needed to picture why it does it. And when he found his answer, it came from the one place nobody had thought to look, from the strange, flickering world of the very small. Part 7. Every path at once. The mind that finally answered the question Einstein left open belonged to a physicist who never trusted an equation until he could picture what it was actually saying. His name was Richard Feynman, and where other physicists saw abstract symbols on a page, he saw processes unfolding, particles doing things, the universe quietly telling a story that the mathematics was only trying to transcribe. He had a restless, almost mischievous need to understand things from the ground up, to take a piece of reality apart in his imagination and see how it truly worked. And one deceptively simple question fascinated him more than almost any other. When a particle travels from one point to another, what path does it actually take? Classical physics had a comfortable answer, the same one your intuition would give. A particle follows one path, a single definite route, determined by the forces acting on it. Throw a ball across a room and it traces one clean arc through the air. Fire a bullet and it follows one trajectory. Give the starting conditions and the path is fixed and singular and knowable. For everyday objects, this works so well that it never occurs to us to doubt it. But down in the quantum world, at the scale of electrons and photons and the smallest pieces of reality, this comfortable picture falls completely apart, and what replaces it is one of the strangest ideas in all of science. In the quantum world, particles do not behave like tiny balls carving single clean lines through space. They behave like waves, spread out and blurred and uncertain, capable of overlapping and interfering with themselves. And so, when a particle travels from a point we will call A to a point we will call B, it does not, according to Feynman, take one route. It takes every route. Not as a figure of speech, not as a fuzzy approximation, but literally. The straight path and the curving path, the smooth trajectory and the violent zigzag, paths that loop backward on themselves, paths that wander far out to the side, paths that go swinging out toward the edge of the galaxy before doubling back to arrive at their destination. Every conceivable route the particle could take from A to B, no matter how sensible or how absurd, is somehow included in what actually happens. Feynman called this the sum over histories, and it is his most famous and most radical idea. The particle explores all its possible histories at once. When you first hear this, it sounds not just strange, but impossible, even nonsensical. How can one particle take every path? The answer lives in the quantum idea of superposition. Before a particle is measured, before it is pinned down, it does not possess a single definite history the way a thrown ball does. It exists instead as a whole spread of possibilities, all coexisting, each one contributing something to the final result we eventually observe. And here is the machinery that makes it work, the part that turns this wild idea into the most precise physics ever devised. Each possible path carries with it a quantity called a probability amplitude, and you can picture that amplitude as a tiny arrow or the hand of a tiny clock that has both a size and a direction. The direction, what physicists call the phase, is set by how the particle moves along that particular path. As the particle sweeps along each route, its little clock hand spins, and it arrives at the destination pointing some particular way. Now, these arrows do not simply pile up and add together the way ordinary numbers do. They combine like arrows, tip to tail, and this is where something miraculous happens, where order comes out of the apparent chaos. For the wild, absurd paths, the violent zigzags and the far detours, the clock hands spin at wildly different rates and arrive pointing in every possible direction. When you add up a huge collection of arrows all pointing randomly this way and that, they cancel each other out almost perfectly. For every arrow pointing one way, there is another pointing the opposite way, and their contributions annihilate. So all those strange, looping, faster and slower paths taken together contribute essentially nothing. They erase themselves. But the paths that stay close to the sensible classical route, the smooth, efficient path a thrown ball would follow, share nearly the same phase. Their little arrows all point in nearly the same direction, and when you add them up they reinforce one another, piling into a strong combined arrow that survives. And so the single path we actually see, the classical trajectory, is not chosen because some law commands it. It emerges, all on its own, because it is the path where the arrows agree, the path that survives the great cancellation while all the alternatives wipe themselves out. Let yourself shrink down and watch this happen, because it is a sight worth witnessing in your mind. Imagine you could stand beside a single electron as it leaves point A, and imagine you could see what it really does. Instead of one line shooting toward B, it blooms outward into a shimmering fan of every possible route at once. There is the straight path, and beside it the gentle curve, and beside that a jagged zigzag, and beyond that a wild loop that swings out impossibly far before returning, all of them happening together, each one carrying a tiny spinning arrow of light. Now watch the arrows. Out along the wild paths they whirl and scatter, pointing every direction at once, and as you add them together they fold into nothing, cancelling into silence. But along the sensible paths near the centre, the arrows swing into alignment, all pointing nearly the same way, and they stack up into something solid and bright. The single glowing line that remains, the one path left standing after that silent vote no one organised, is the path you would have called the only path all along. Reality, it turns out, is what is left over after nearly everything cancels out. If this sounds too abstract to believe, there is a famous experiment that shows it happening, and you may have heard of it. Send particles, one at a time, toward a barrier with two narrow slits cut into it, and let them land on a screen behind. Each particle strikes the screen at a single point, like a tiny pebble, but let thousands of them go through, one by one, and a pattern gathers on the screen, a series of bright and dark bands, exactly the pattern you would get from waves passing through both slits at once and interfering. The astonishing part is that this happens even when the particles go through one at a time, with long gaps between them, so that each particle could only have interfered with itself. In the sum over history's picture, this is precisely what you would expect. Each particle explores every path to the screen, including paths through both slits, and those paths interfere, some reinforcing and some cancelling, building the bright and dark bands. The single particle really does, in a sense, pass through both slits at once, because it takes every route, and the pattern on the screen is the visible fingerprint of all those paths adding themselves up. This was the kind of thing Feynman lived for, taking a result that made other physicists uneasy, and finding the picture underneath that made it make sense. He was famous for refusing to accept any piece of physics until he could see it, until he could build a mental image of what the equations were actually describing. In his own popular lectures he explained his method with almost childlike simplicity, talking about little arrows, one for each path, that you add up tip to tail, the final combined arrow telling you how likely the whole process is. No mysticism, no hand-waving, just arrows and addition, applied to every possible history and summed together. It sounds almost too simple to be the foundation of the most accurate physical theory ever tested, and yet it is. The predictions that come out of adding up these arrows match experiment to a precision, something like measuring the distance across a continent and being wrong by less than the width of a human hair. Whatever else you make of the strangeness, the method works, flawlessly, every time, and that is exactly why we have to take seriously what it says about the paths that would carry a particle past the speed of light. There is something genuinely moving about this picture, once it settles in. We walk through the world seeing single, definite things following single, definite paths, and we assume that is simply how reality is put together. Feynman showed us that underneath, the universe is doing something far richer and stranger. Every particle that reaches your eye, every atom in your body, arrived at its place not by taking one road, but by quietly exploring every road there is, and letting all but the surviving few erase themselves. The solidity and definiteness of the world you experience is not a given. It is an achievement, a result, the leftover of a cosmic sum in which almost every possibility votes itself out of existence. The ground you stand on is stable because of a cancelling and a reinforcing happening constantly, invisibly, beneath everything. But I have been holding something back, the reason this strange accounting matters so much for our story. Hidden inside this process, inside the way those little arrows spin and cancel and survive, is the true explanation for the speed of light. The barrier we slammed into with our impossible starship, the wall Einstein described so precisely but could not explain, is sitting right here in Feynman's sum over histories, waiting for us to look closely enough, because among all those infinite possible paths the particle explores, there are some that would require it to move faster than light, and what happens to those paths when the arrows are added up is the most elegant answer to our question that anyone has ever found. Part 8. Why the forbidden paths erase themselves. To see where the speed limit is hiding, we have to look a little closer at how each path's little arrow gets its direction. The spin of that arrow, the phase, is set by a quantity physicists call the action, and the action is a way of measuring how the particle moves through both space and time along a given path. You do not need the equations to feel what matters here. For a particle moving in a way that respects relativity, the speed of light sits right inside that action, woven into it, linking distance and duration together into the single fabric of space-time that Einstein revealed. The action is where a path's journey through space and its journey through time get combined into one number, and that number sets which way the little arrow points when the particle arrives. Now watch what happens when one of those infinite possible paths includes a stretch where the particle moves faster than light. Along an ordinary path slower than light, the action produces a phase that changes smoothly, the arrow spinning at a sensible rate as the particle moves. But the moment a segment of the path crosses into faster-than-light motion, the mathematics of the action changes character completely. Instead of producing a smoothly turning arrow, it produces something that oscillates infinitely fast. The phase along that forbidden stretch spins with unlimited speed, the arrow whirling around so violently, so uncontrollably, that no two nearby faster-than-light paths ever point the same way. And you already know what happens to a collection of arrows pointing in every possible direction. They cancel, completely, perfectly. When you add up all the paths that involve faster-than-light motion, every one of their contributions annihilates against another with absolute precision, not approximately, not statistically, but exactly. Sit with what this means, because it is the answer we have been travelling toward this whole time. The faster-than-light paths are not banned. Nobody posted a rule forbidding them. There is no cosmic barrier, no wall, no security guard turning particles away at the edge of light speed. Those paths are perfectly allowed to exist in the mathematics. The particle does explore them, in exactly the same way it explores every other path. It is just that when the great sum is taken, when all the arrows are added together, the faster-than-light contributions cancel themselves into nothing. They are present, and they contribute exactly zero. There is a beautiful and very old idea hiding inside this, one that reaches back long before quantum mechanics, and it is worth seeing. Centuries ago, people noticed that light seems to travel in a way that is somehow efficient. It goes in straight lines through empty space. When it bends as it passes into water, it bends by just the angle that carries it to its destination in the least possible time. It was almost as though light sniffed out the quickest route and took it, which seemed a little eerie, as if the beam somehow knew where it was going before it set out. For a long time, this principle of least time was a curiosity with no explanation. Feynman's sum over histories finally supplied one. Light does not know anything in advance. It takes every path, as everything does. But the path of least time, the efficient one, is special in a particular way. Near that path, small changes barely affect the travel time, so all the neighbouring paths share almost the same phase, and their little arrows line up and reinforce. Away from it, the travel time changes quickly from one path to the next. The arrows scatter in all directions and they cancel. So the efficient path is simply the one that survives, the place where the paths agree with one another, and that is why light appears to choose it. The same logic governs the speed limit itself. The paths that stay below light speed can agree with their neighbours, share a phase, and reinforce, so they survive the sum and become the reality we see. The paths that break past light speed cannot agree with anything at all, because their arrows spin without limit, so they cancel down to nothing. The ordinary world, the world of definite paths and reliable motion, is not stamped onto the quantum blur by some outside rule. It condenses out of the blur wherever the paths can agree, and it simply never forms where they cannot. The speed of light marks the exact edge of that agreement, the boundary past which no collection of paths can ever line up. That is why the barrier is so perfectly sharp, so absolute, and so utterly without exceptions. It is not policed by anyone. It is the natural fault line where the very possibility of a coherent story runs out. They exist in the accounting, and they leave no trace whatsoever on reality. Nothing outruns light, not because the universe prevents it, but because faster-than-light histories erase themselves before they can ever add up to anything real. This is the quantum origin of the speed limit, and I want you to feel the difference between what Einstein gave us and what Feynman gave us, because it is the whole point. Einstein showed us how the barrier works. He showed us that reaching light speed would demand infinite energy, that time would freeze and lengths would vanish, that the wall is unclimbable. He described the barrier in perfect, unforgiving detail. But Feynman answered a deeper question. He showed us why the barrier is there at all. It is there because reality is assembled only from the paths that survive the sum, and faster-than-light paths cannot survive. The universe does not forbid faster-than-light motion. It does something far more absolute than forbidding. It refuses to give faster-than-light motion any meaning at all. And that, I think, is one of the most quietly staggering ideas a person can hold in their mind. We spend so much time imagining the speed of light as a wall, as a thing standing in our way, as an obstacle that a clever enough species might one day find a way around. Feynman's picture dissolves that image entirely. There is no wall to get around because there was never a wall. There is only a sum taken across every possibility, and the possibilities that would carry us past light speed are the ones that cancel themselves into silence. Reaching beyond light speed is not like trying to break through a barrier. It is like trying to find a number between two numbers that have nothing between them. The territory you are reaching for does not exist to be reached. It was never held back from you. There was simply never anything there. The barrier is absolute precisely because it is not a barrier. It is an absence, a place where the universe declines to build anything real. Feynman turned this insight into a practical tool, one that transformed physics. He developed a way of drawing simple pictures, little diagrams of lines and vertices, each one representing a class of these paths, a possible way for particles to move and interact. You add up all the allowed diagrams, all the possible stories of how an interaction could unfold, and the universe tells you what can actually happen. These diagrams became the working language of modern particle physics, the everyday bookkeeping of the quantum world, and they carry this same underlying logic inside them. Nature does not select one single narrative for how an event plays out. It considers every conceivable narrative, sums them all together, and keeps only those that remain self-consistent. The faster-than-light stories are always in the pile, they always cancel, and this is exactly why the apparent loopholes people dream up keep failing in the same frustrating way. Certain quantum calculations seem, at an intermediate step, to let particles slip past the limit, in the form of what physicists call virtual particles that flicker in and out of the math. But their unphysical, faster-than-light behavior always, without exception, cancels out by the time you reach the final answer. The limit is not enforced by physicists insisting on it. It enforces itself automatically through interference, everywhere, for free, at every scale, in every calculation. The human meaning of this is worth pausing on, because it reframes something we tend to experience as a disappointment. We often feel the speed of light as a kind of cosmic cruelty, a locked door between us and the stars, a limit imposed on our ambition by an indifferent universe. But Feynman's answer tells us the limit was never imposed on us at all. It is not a rule handed down from above and enforced against our will. It is a natural, inevitable consequence of the way reality adds itself up, the same process that makes the ground solid and the world definite and the classical path emerge from the quantum blur. The speed limit and the stability of everything you know are the same phenomenon. You cannot have one without the other, and that means the barrier keeping us below light speed is woven from the very same fabric that lets there be a coherent universe for us to be ambitious in. It is not a wall built to keep us in. It is a thread in the weave that lets us exist at all. And once you truly see that, every clever scheme anyone has ever proposed for cheating, the limit starts to look different, because you begin to understand why each one is doomed before it starts. Part 9. Every loophole closes. Once you understand that faster-than-light histories simply erase themselves from reality, a strange kind of pattern starts to make sense. For more than a century, some of the most creative minds in physics have gone hunting for loopholes, for some clever way to sneak past the speed of light without technically breaking it. And over again, in domain after domain, they have run headlong into the same wall, or rather, into the same absence where a wall appears to be. Every proposed shortcut, when you follow it all the way through, either collapses into physical impossibility or destroys the logic of cause and effect so completely that it cannot be allowed to exist. Let me walk you through a few of the most famous attempts, because seeing them fail, one after another, is how you come to feel just how total the limit really is. Start with a particle that was dreamed up specifically to beat the limit, the tachyon. The idea was elegant in its symmetry. Ordinary particles always move slower than light and can never be pushed up to light speed. So physicists imagined a mirror image particle that always moves faster than light and can never be slowed down to light speed. It would live its whole existence on the far side of the barrier, never crossing, just as we never cross from our side. On paper it seemed almost reasonable, but the tachyon came with a fatal flaw baked into its nature. In some frames of reference it would appear to move forward in time, and in others it would appear to move backward. Its energy could become negative. Signals carried by tachyons could arrive before they were sent. The mathematics would only permit tachyons to exist at the cost of shattering cause and effect, and no experiment has ever detected the slightest trace of one, and no consistent theory has ever managed to include them without generating paradoxes. Tachyons remain what they always were, a mathematical curiosity that serves mostly as a warning sign, a marker of the territory where physics stops making sense. Then there is quantum tunneling, which for a while looked like it might offer a real escape. In certain experiments, a particle crossing a barrier seems to appear on the far side sooner than light could have made the same trip, and headlines have more than once announced that the speed of light had been beaten. But the illusion dissolves under careful examination. Information is not carried by the peak of a wave, the part that seems to arrive early. It is carried by the leading edge, the very first hint of the signal, the first disturbance that could possibly encode a message. And that leading edge never outruns light. What tunneling does is reshape the wave, shifting its peak forward, making it look as though something arrived early, without ever actually transmitting information faster than light. Every careful measurement confirms it. The message, the thing that could actually carry cause from one place to another, stays under the limit. Quantum mechanics guards causality with a ruthless, almost suspicious consistency. You can push on this loophole as hard as you like, and it holds. Experimenters have measured pulses of light that appear, by the timing of their peaks, to have crossed a barrier faster than light could, an effect with its own name in the physics literature. Every single time, careful analysis reveals the same thing. The peak of a pulse is not a messenger. You cannot ride it, cannot load information onto it, cannot use it to tell a distant friend anything at all, because that peak is only the crest of a shape that was already spread out across space before it arrived. The part of the pulse that could actually carry a signal, its very leading edge, the first faint stirring that was not there a moment before, never crosses faster than light. It cannot, because that leading edge is where genuinely new information lives, and new information is exactly what the speed limit protects. What looks like a faster-than-light arrival is always a reshaping of something already present, a rearrangement of a wave that was partly there all along, never the delivery of a fresh message ahead of schedule. The universe lets the crest appear to cheat, and quietly makes certain the messenger never does. Over and over, in experiment after experiment, across decades of increasingly clever attempts, the same pattern holds without a single exception, and it is precisely the pattern Feynman's sum predicts, because the information carrying front of any signal is built from exactly the paths that can never outrun light. Some dreamers aimed higher, trying not to move through space faster than light, but to bend space itself. In the year 1994, a physicist named Miguel Alcubierre proposed something that thrilled science fiction fans everywhere, a genuine warp drive that lived within Einstein's own equations. The idea was clever. Instead of pushing a ship through space faster than light, which we know is impossible, you would contract space in front of the ship and expand it behind, so the ship would ride a moving bubble of space-time, like a surfer carried along by a wave. Locally, inside its bubble, the ship would never exceed light speed at all, so it would seem to slip through the loophole. On paper, the equations allowed it. Reality did not. To create such a bubble, you would need enormous quantities of exotic matter, a bizarre substance with negative energy that repels rather than attracts, and the amount required is not merely impractical. It exceeds the total energy content of the entire observable universe. Even setting that aside, later analysis revealed the bubble would sweep up radiation and particles to catastrophic intensities, and when it stopped, that stored energy would burst out in a flash powerful enough to scour clean any world at the destination. Worse still, the people inside the bubble could not even control it. because signals from within cannot reach the bubble's leading edge faster than light. The warp drive is a fascinating piece of mathematics and a physical impossibility, and the reason it fails traces straight back to the same source. Cross the limit in any real way and you break the universe. Wormholes offer another tantalizing escape, a tunnel through space-time connecting two distant places, so that you might step in near Earth and step out beside another star without ever travelling faster than light through the tunnel itself. Einstein's equations do permit such shapes under special conditions, but once again, holding a wormhole open requires that same exotic matter with negative energy, and without it the tunnel snaps shut instantly. And if you did manage to hold one open, you would find you had built something even more dangerous than a shortcut. A wormhole you can travel through can always be turned into a time machine, producing exactly the same paradoxes, the same collapse of cause and effect as any other way of beating light. Nature, it seems, has arranged things so that every road leading past the speed of light runs directly into contradiction, and the universe does not tolerate contradiction. Now let me put you inside the paradox so you can feel why the universe guards against it so fiercely. Imagine you hold a device that can send a message faster than light, and you press the button. From where you sit, the message simply races off toward its destination, ordinary enough. But because observers moving at different speeds genuinely disagree about the order of widely separated events, there will always exist someone, gliding past in another frame of reference for whom that message arrives before your finger ever touched the button. Picture it from their point of view. They watch the receiver light up with your message, complete and delivered, and only afterward do they see you reach out and decide to send it. The reply comes before the question. The effect comes before the cause, and if the message can arrive before it was sent, then it could carry a warning about a choice you have not yet made, letting you change your mind and never send it, which means it was never sent, which means you were never warned. The whole chain of cause and effect eats its own tail. This is not a puzzle waiting to be cleverly solved. It is a logical contradiction, and it falls directly out of the equations the moment you allow anything to outrun light. There is one more phenomenon I have to mention, because it is the one people most often think breaks the rule, and it is quantum entanglement. When two particles are entangled, measuring one seems to instantly determine the state of the other, even if they are on opposite sides of the galaxy. Einstein himself was troubled by it, and called it spooky action at a distance. It looks, at first glance, like information leaping across space in no time at all. But it is not. When you measure your entangled particle, the outcome you get is completely random. You cannot choose it, cannot control it, cannot use it to encode a message. The distant partner, measuring their particle, also sees nothing but randomness. Only later, when the two of you compare your results using an ordinary signal that crawls along at or below light speed, do the correlations reveal themselves. No message ever outran light. Entanglement creates correlation, not communication, and physicists have proven this so rigorously it has a name, the no-communication theorem. Even quantum mechanics, which flirts with so much strangeness, stops precisely at the line where causality would break. I will give the universe's stubbornness one final, almost comic illustration. In the year 2011, an experiment appeared to catch neutrinos travelling faster than light, and for a few electric months the world wondered whether the great limit had finally cracked. Physicists chased the result with everything they had, because that is what good scientists do with a genuine anomaly. And in the end, the faster-than-light neutrinos turned out to be the product of a loose fibre optic cable and a timing error. Tighten the connection, and the neutrinos fell right back in line, obeying the limit exactly. It is almost funny, and it is deeply telling. Every real anomaly that has ever seemed to beat light has been chased down and has resolved, without exception, back to the same unbreakable speed. The loopholes close, every single time, and they close for the reason Feynman uncovered. But if the limit protects itself this fiercely, across every scale and every clever scheme, then it must be protecting something precious, something the universe cannot function without, and it is. What the speed of light truly guards is not a number at all. It is the difference between before and after. Part 10. The speed of cause and effect. Up to now, we have mostly treated the speed of light as a barrier to motion, a limit on how fast things can travel, enforced by swelling energy and freezing time and the quiet cancellation of forbidden paths. But the true reason the universe guards this limit so fiercely has almost nothing to do with travel, and everything to do with something far more fundamental. To see it, we have to stop thinking about rockets and particles for a moment and start thinking about the relationship between events, about how one thing is allowed to cause another. In Einstein's universe, space and time are woven together into a single fabric, and within that fabric, not every pair of events is connected in the same way. Some events can influence one another, and some cannot, and the line between the two is drawn by exactly one thing: the speed of light. If one event is close enough to another in space, and far enough apart in time, that light could travel between them, then the first can be a cause of the second. They are causally connected, and here is the crucial part: every observer in the entire universe, no matter how they move, agrees on their order. The cause always comes first. On that, the whole cosmos is unanimous. But if two events are separated by a great deal of space and only a little time, so far apart that not even light could bridge the gap between them, then something remarkable happens. Those two events cannot affect each other at all, and because no influence can pass between them, different observers moving at different speeds will actually disagree about which one happened first. One observer sees event A before event B. Another, gliding past at a different speed, sees B before A. A third sees them happen at the very same instant, and astonishingly, none of them is wrong. This is not a flaw in anyone's instruments or a trick of perception. It is built into the structure of space-time itself, and it goes by the name of the relativity of simultaneity. The word now, it turns out, is not universal. Your now and the now of someone speeding past you slice through the fabric of events at slightly different angles, and for events far enough apart, your slices can put them in different orders. Normally this causes no trouble whatsoever, and you never notice it, precisely because those disagreements only ever happen for events that cannot influence each other in the first place. Nothing passes between them, no signal, no cause, no effect, so their disputed ordering never leads to any contradiction. The universe can afford to let observers disagree about the order of events that have nothing to do with one another, because that disagreement can never come back to bite it. But now you can see the trap that faster-than-light travel would spring. The instant you allow anything, a ship, a signal, a single bit of information, to cross that gap faster than light, you connect two events that the universe had carefully kept disconnected. You reach into the region where observers disagree about the order of things, and you force a cause and an effect across it. And since some observers see that crossing running one way in time, and others see it running the other way, you have created a situation where, for somebody, the effect happens before the cause. Faster-than-light motion, worked out in full, is mathematically identical to sending information backward in time for some observer. It is not a separate danger. It is the same thing wearing a different mask. Let me make the danger concrete, because it is easy to nod along to the idea of backward causation without feeling how genuinely absurd it would be. Imagine you had a phone that could send a message instantly across any distance, faster than light, with no delay at all. It sounds like the greatest invention in history, and it would be the end of the universe as a place that makes sense. Here is why. Because observers moving relative to one another truly disagree about the timing of far-apart events, your instant message, sent to a friend on a distant world, could be arranged so that, from the point of view of someone gliding past you, it arrives before you sent it. Now let your friend, on receiving it, instantly send a reply, timed the same way. That reply can arrive back to you before you sent your original message. You could, with a little arithmetic, receive the answer to a question you have not yet asked. You could learn the winner of a race before you placed your bet, place the bet accordingly, and change the outcome so that the result you were told was never the result at all. These are not clever puzzles with hidden escape hatches. They are contradictions, plain and simple, statements that both are and are not true at the same time, and a universe that permitted them could not hold together for a single instant. Physics would lose the ability to say that anything follows from anything else, because the future could always reach back and unmake the past that produced it. This is what the speed of light quietly prevents, every second, everywhere, without ever being thanked for it. It guarantees that when two things are genuinely linked as cause and effect, everyone, everywhere, in every state of motion, agrees on which one came first. It permits the universe to disagree only about the ordering of events that can never touch, where the disagreement is harmless and leads nowhere. The limit is the thin invisible membrane that keeps cause on one side and effect on the other, and it never tears. That is what you would be breaking, not a speed record, but the very possibility of a story that holds together. And once you see that the price of outrunning light is a universe where an effect can erase its own cause, the barrier stops looking like a cruelty and starts to look like a mercy, the one rule that lets there be any reliable order at all. And once information can travel backward in time, cause and effect stop meaning anything at all. You could receive a warning about a decision you have not made and use it to make a different decision, so the warning is never sent. You could witness the consequence of an action whose cause lies in the future. You could build loops where a piece of information causes itself, arising from nowhere, with no origin anywhere in time. These are not intriguing philosophical puzzles with clever resolutions. They are flat logical contradictions, and a universe that permitted them could not hold together as a coherent place where anything reliably follows from anything else. I want you to feel the weight of what that means, because this is the moment the whole story turns, the place where the speed of light stops being about speed at all. The limit is not really there to stop you from going fast. It is there to protect the difference between before and after. It is the thin, invisible thing that guarantees that causes come before their effects, that the past stays settled while the future stays open, that a warning cannot arrive before the danger, that a memory records what has happened and not what is going to happen. Strip that protection away, and it is not just travel that breaks, it is meaning itself. A universe where effect can precede cause is a universe where nothing can be counted on, where the future can reach back and rewrite the past, where the very idea of one thing leading to another dissolves into noise. Everything you are, every thought you have ever finished, every choice that led to another choice, depends on cause coming before effect. The speed of light is what keeps that true. It is not the guardian of a speed record. It is the guardian of the logic that lets there be a coherent story at all. And this is why every loophole we explored had to fail, why the tachyons and the warp bubbles and the wormholes and the faster-than-light signals all collapse into contradiction the moment you examine them closely. They do not fail because we are not clever enough, or because the engineering is too hard, or because we have not yet found the trick. They fail because succeeding would mean a universe that cannot define before and after, and such a universe cannot consistently exist. Feynman's cancellation of faster-than-light paths and this protection of cause and effect are not two separate facts. They are one single fact seen from two sides. The forbidden paths erase themselves in the quantum sum for the very same reason that faster-than-light signals would shatter causality and relativity. The universe is built, at its foundations, to allow only the histories that hold together, the stories where cause reliably precedes effect, and it quietly refuses to assemble any of the others. The human stakes here could not be more intimate. Your memory works because causes come before effects, laying down a record of a past that is fixed and a future that has not yet arrived. Your very thoughts work because signals travel in sequence through the neurons of your brain, one firing leading to the next, cause before effect, all the way down. Consciousness itself, the fact that you are here, following this, one moment leading into the next, depends on living in a universe where information cannot arrive before it was created. The speed of a light protects that structure at every level, from the interactions of particles to the firing of a single neuron to the turning of an entire galaxy. It is the reason your life has an order, the reason your story runs forward. But if the limit does all this, if it draws the line between what can influence what across the whole of reality, then it must also be drawing that line at the grandest scales imaginable, out where whole regions of the universe fall forever beyond each other's reach. And that is where we go next, to the places where cause and effect finally run out. Part 11. Where cause and effect end. If the speed of light draws the boundary between what can influence what, then that boundary does not stop at the scale of laboratories and starships. It extends outward, all the way to the largest structures in existence, and at those scales it takes on a character that is almost overwhelming to contemplate. Every event in the universe, including this very moment wherever you happen to be, sits at the center of a kind of shape, a boundary in space-time that physicists call a light cone. Reaching back into the past, your light cone contains every event that could possibly have influenced you, everything whose light or signal has had time to reach you. Reaching forward into the future, it contains every event you could ever possibly affect, everywhere your influence could still travel, and everything outside those two cones is simply beyond you, unreachable and unreachable from, causally severed, as though it belonged to a separate world. The speed of light sets the slope of those cones, decides which events can be your causes, which can be your effects, and which are forever strangers to you. This is not abstract geometry. It is the actual architecture of what can touch what, drawn across all of reality by a single number. Nowhere does this become more vivid or more unsettling than at a black hole. When a massive star exhausts its fuel and collapses under its own gravity, it can curve space-time so sharply that a boundary forms around it, a surface called the event horizon. At that surface, the speed you would need to escape becomes equal to the speed of light itself, and because nothing with mass can reach light speed, nothing with mass can escape once it crosses that line. But the truest way to understand a black hole is stranger and more beautiful than just thinking of it as a place where gravity is too strong. Inside the horizon, space-time is tilted so severely that the singularity at the center no longer lies in some direction you could steer away from. It lies in your future. Falling toward it becomes as unavoidable as falling toward tomorrow. No matter which way you turn, every possible path leads forward to it, because it sits in the future of every direction you could move. Escaping the black hole would require traveling into your own past, and the same speed limit that forbids faster-than-light motion forbids exactly that. A black hole, in the end, is not so much a pit you fall into as a place where the future itself points only one way. Let yourself cross that boundary in your imagination, gently, because it is not the violent thing you might expect. Picture yourself drifting toward a large black hole, and as you approach the event horizon, there is no wall, no barrier, no sudden jolt. For a large enough black hole you could pass through the horizon and feel nothing at all in that instant, nothing to mark the most important crossing of your life, and yet everything has changed. A moment before, the center was a place ahead of you in space, somewhere you could in principle turn away from. Now it is a moment ahead of you in time, as certain and as unavoidable as the next tick of a clock. Every direction you look, every way you might thrust or turn, leads there, because forward in time is the only direction that exists for you now. To escape would mean moving backward through time, and the universe simply does not permit it. The horizon was never a wall you struck. It was the edge of cause and effect itself, the place where your future collapsed down to a single destination. And the same speed of light that shapes the humblest interaction between two particles is what carved that one-way boundary into space-time. That same principle draws an edge around everything we can ever see. Our universe is about 13.8 billion years old, which means light has only had that long to travel toward us since the beginning. You might expect, then, that we could see about 13.8 billion light-years in every direction and no further. But the true edge of the observable universe lies much further out, roughly 46 billion light-years away in every direction. That startling difference exists because space itself has been stretching and expanding this entire time. Light that set out toward us billions of years ago has been crossing a cosmos that kept growing beneath it as it travelled, so that the places those ancient beams came from have since been carried far, far away. Beyond that immense boundary lie regions we will never see, not because light is too slow to have reached us, but because the expansion of space means their light will never arrive at all. Those distant places are not merely far away, they are severed from us in cause and effect. Nothing that happens there can ever reach us, and nothing we do can ever reach them. And this severing is not finished. It is slowly getting worse, on a timescale that dwarfs the whole of human history. The expansion of the universe is not merely continuing but speeding up, driven by something we still barely understand, and as it accelerates, the boundary of what we can ever reach draws steadily inward. There is a distance, called the cosmic event horizon, beyond which galaxies are being carried away from us so quickly by the stretching of space itself, that any light they send out from this moment onward will never arrive. Those galaxies do not suddenly go dark. We still see their old light, the ancient messages already in flight toward us. But we're seeing their past, and we will never see their present or their future, because the space between us is growing faster than their new light can cross it. One by one, across billions of years, the galaxies we can see are drifting across that line and passing out of our reach forever. In the far, far future, an astronomer on some world orbiting some distant star will look out and find almost nothing beyond their own gathered island of galaxies, the handful bound together tightly enough by gravity to resist the expansion. All the rest will have slipped over the horizon, their light stretched away into nothing. That future astronomer, doing careful and honest science, would have no way of knowing that a wider universe of hundreds of billions of galaxies had ever existed, because every trace of it would lie beyond the reach of cause and effect. It is a strange and slightly haunting thought that the universe is quietly editing itself down, closing like a book, one region at a time. But it also says something tender about the moment we happen to occupy. We exist early enough, in cosmic terms, that the light of that wider universe still reaches us, that the sky is still crowded with far-off galaxies we can study and wonder at. We are living inside a window, a long one but not an endless one, when the universe is still legible, when the past of nearly everything is still arriving overhead. The same speed of light that will one day close the sky is the reason we can read it so fully now, and there is a quiet gratitude available in that if you go looking for it. They lie outside our light cone permanently, and no ship and no signal and no patience will ever change it. And here that phrase I asked you to remember comes back with its full weight. Looking into space is looking into the past. When Römer first proved that light takes time to travel, it meant the sun we see is 8 minutes old. But stretched across the entire cosmos, that same simple truth becomes something enormous. The night sky is not a picture of the universe as it is now. It is a layered archive of countless different times, all stitched together and arriving at your eye in a single instant. The nearby stars show you light that is years or centuries old. The faint smudges of distant galaxies show you light that left them billions of years ago. Images of a universe that no longer exists in that form, frozen and delivered to you across an almost unthinkable gulf. You're not seeing the cosmos. You're seeing its history, every point in the sky reporting from a different moment in the past, and the deeper you look, the older the news. The finite speed of light does not just delay what we see, it turns the whole sky into a museum of moments that will never come again. There is a loneliness in this that is worth sitting with, though it is not a loneliness that should frighten you. As the expansion of the universe accelerates, that cosmic isolation is slowly deepening. Distant galaxies are drifting beyond our reach even now, crossing that final boundary one by one, their light stretching and fading until it can no longer arrive. In the far future, astronomers, if any exist, will look out and see only the handful of galaxies gravitationally bound to our own local neighborhood. Everything else will have slipped away, carried off by expanding space, erased from view not by darkness, but by the geometry of space-time and the finite speed of causality that governs it. The universe is quietly closing itself off, region from region, drawing each patch of existence into its own separate island. And it is the speed of light, the same number we have followed all this way, that sets the size of those islands and the walls between them. It sounds like the saddest fact in cosmology. But as we are about to see, without exactly this limit, without this finite speed of cause and effect, there would be no islands and no observers and no galaxies and no stars to grow lonely in the first place. The very thing that separates us is the thing that let there be in us at all. Part 12. The frame rate of the cosmos. We have travelled a long way to arrive at a single quiet turn, and here it is. When physicists say that nothing can move faster than light, it is easy to hear that as a limitation, a ceiling clamped down on motion and ambition and reach, a rule that hems us in. But by now I hope you can feel that the truth runs the other way entirely. The speed of light is not a restriction placed on the universe from outside. It is the structure that lets the universe be a universe at all, and to see why, we only have to ask what would happen if there were no such limit. Imagine a cosmos in which influence travelled instantly, in which any event could affect every other event with no delay whatsoever. It sounds freeing at first, a universe with no barriers. But think about what it would actually mean. Every region of space would immediately equalize with every other. Any difference in temperature would vanish in an instant as heat rushed everywhere at once. No gradient could persist, no structure could hold, because the moment any imbalance formed, it would smooth itself away across the whole of existence with no time to spare. Stars could not burn slowly and steadily for billions of years, doling out their energy across the ages, because there would be no such thing as slowly. Chemistry could not stabilize long enough to build anything, because every reaction would reach everywhere before it could settle. A universe with no speed limit is a universe with no delays, and a universe with no delays is a universe that equilibrates into featureless sameness instantly and stays that way forever. It is the finite speed of causality that gives reality room to have structure, to hold differences long enough for something interesting to happen, to let cause take its time turning into effect. The delays are not a flaw. The delays are what make everything possible. This same finite speed even shapes the arrow of time itself, the reason time seems to flow in one direction. Most of the fundamental equations of physics work equally well run forward or backward, and yet our experience has a clear direction. We remember the past and not the future. Disorder tends to increase, spreading outward, never spontaneously gathering itself back up. That one-way flow is tied to how information spreads through the universe, and information cannot spread faster than light. The finite speed of causality sets the pace at which order dissolves into disorder, the tempo at which the past becomes the past. Memory is possible because causes come before effects, laying down records in one direction only. Thought is possible because signals move in sequence, one step leading to the next. The forward flow of your own experience, the very sense that you are moving through time from a remembered past into an open future, rests on the fact that the universe has a finite speed of causality and honors it without exception. And this is why so many physicists say, quietly and a little insistently, that the speed of light is badly named. It is not really about light at all. It is the speed of causality, the maximum rate at which cause can become effect, the conversion factor between space and time, the tempo at which reality is allowed to update itself. In the geometry of space-time, distance and duration are not truly separate things. They are two different ways of measuring the same underlying fabric, and the speed of light is the number that translates between them. 1 second of time corresponds to about 300,000 kilometers of space. Turn that sentence over in your mind, because it is stranger and more profound than it first sounds. We are used to treating time and space as completely different kinds of things, one measured in seconds and the other in kilometers, one flowing past us whether we like it or not, and the other laid out around us to move through as we please. But the speed of light is a bridge between the two, a fixed exchange rate that says a second and 300,000 kilometers are, in a real sense, the same amount of space-time only counted in different currencies. When physicists set the speed of light equal to 1 in their equations, they are simply choosing to measure time and space in the same units, and the moment they do, the artificial wall between the two dissolves and the single underlying fabric shows through. Moving through space and moving through time stop being separate activities and become two directions through one unified thing. And this very same exchange rate is the one sitting quietly inside the most famous equation ever written, the one relating energy to mass. When you multiply a mass by the speed of light multiplied by itself, you're running that enormous conversion factor twice over, and the result is that even a tiny amount of matter is equivalent to a staggering amount of energy. This is why the sun can pour out light for billions of years by converting only a small fraction of its mass each second, why a pinch of matter holds the energy of a city. Mass and energy are not two separate things that happen to be related. They are the same thing, measured in different units, and the number that translates between them is the speed of light, the same number that sets the slope of the light cones and the tempo of cause and effect and the size of everything we can see. Everywhere you look in physics, at every scale from the particle to the cosmos, this one constant keeps appearing, not because light is special, but because the number was never really about light in the first place. It is the conversion rate of reality itself, the single tempo that ties space to time and mass to energy and cause to effect. That is not a statement about how fast anything moves. It is a statement about the exchange rate between the dimension we call time and the dimensions we call space. This is why physicists so often simplify their equations by setting the speed of light equal to 1, treating a second and 300,000 kilometers as the same measurement in different units. Doing so strips away the illusion that space and time are fundamentally different kinds of things, and reveals them as aspects of one unified whole. And this very same conversion factor is the one hiding in Einstein's most famous equation, the relationship between energy and mass, where the speed of light squared is the rate that turns a tiny amount of matter into an enormous amount of energy. The number we have chased all night is not the speed of a glowing thing. It is the frame rate of the cosmos, the rhythm to which every particle and every force and every interaction quietly keeps time. Now let me bring back the two images I asked you to carry, because they have both been waiting for this moment. Remember Galileo on his hill trying to time a whisper with a clock that ticked like thunder, defeated because his tools were absurdly too crude for what he was chasing. Here at the end, that image turns all the way around. It was never really the lantern that was too crude, or the reflexes, or the hills. It was human intuition itself, our settled and comfortable sense of how space and time ought to behave. That was the thunderous, clumsy clock. Standing beside the true speed of causality, the frame rate of the whole universe, it is we who are the whisper, and our ordinary common sense that ticks like thunder, far too coarse to catch the fine and beautiful structure underneath. Galileo's failure was the first hint of a truth it would take 3 more centuries and 2 of history's greatest minds to finally hear. And remember the wall. Remember sitting in that impossible cockpit with a limitless engine, pressing against a barrier you could not cross, certain there must be forbidden territory just on the other side if only you could break through. Here is the last turn of our whole journey, the one the thumbnail promised you from the very start. It was never a wall. There is nothing on the other side being kept from you, no hidden country past the barrier, no shortcut you were not clever enough to find. Feynman showed us that faster-than-light histories do not slam into a wall, they simply cancel themselves into nothing, contributing 0 to what is real. There is no beyond, and that means the speed of a light was never a wall holding us in. It is a foundation holding everything up. It is the reason stars burn slowly enough for planets to form and life to arise. It is the reason galaxies can evolve instead of collapsing instantly into sameness. It is the reason the past stays fixed while the future stays open. The reason cause can lead to effect. The reason there is an order to things at all. It is not the limit. It is the floor you have been standing on this entire time, the quiet structure beneath every moment of your existence. The universe does not forbid faster-than-light motion out of some cosmic stinginess. It simply cannot build a coherent reality out of the possibilities that would require it, and so those possibilities erase themselves, gently and completely, before they ever become real. This is the strange and profound thing that Feynman helped us see, standing on the shoulders of Galileo and Romer and Michelson and Einstein, and everyone who ever tried to catch light and failed. The speed of light is not the fastest thing in existence. It is the reason existence can happen at all. It is not a barrier between us and the stars. It is the thread that lets there be stars, and a sky to hang them in, and creatures like us who can lie awake beneath them and wonder why the universe is built the way it is. And when you understand that, truly understand it, the limit stops feeling like something holding you back. It starts to feel like the ground beneath everything you are, steady and quiet and holding, the same tonight as it has been since the first light crossed the first stretch of empty space, and the same as it will be long after. Rest easy in it. It is not the limit. It is what makes everything else possible.